So far we've been looking at gas laws where we've kept the mass of the gas or the amount of gas constant. However, having a gas law where we can include the amount of gas that we have and the relationship will be of particular interest for us. So we know three relationships. We know that my pressure is inversely proportional to my volume. We know it's directly proportional to my temperature, and it's directly proportional to my amount of gas. So we have three laws that we looked at. So as a result, we could say that pressure is proportional to my amount of gas times my temperature divided by my volume. If we want to get rid of the proportionality sign, we need a constant. We're going to call the constant in this case R, and then we're going to just take it and rewrite it. And so we're going to rewrite it as PV equals nRT. So my pressure of my gas times the volume is equal to the amount of gas times R, our constant, times the temperature. Okay, and we remember pressure is measured in kilopascals, volume is in liters, N is in moles, T is our temperature in Kelvin. So the question is, what is our R and its value? Well, R is called our ideal gas law constant, but to be in the equation, it has to have a value. Otherwise, it would never cancel out. And we can use a relationship that we know to solve for R. Because we know our definition of our molar volume, we know that any gas occupies 22.4 liters per mole at STP, right? Now we've talked about what STP is, where STP is our standard temperature and pressure, and it refers to conditions where my temperature is 273 Kelvin and 101.3 kilopascals. And because of our definition of molar volume, we know that we have 1 mole, and we have 22.4 liters as our volume of our gas. So we have a relationship between all of our values. This will allow us to solve for the value of R. If we take these values and we substitute them into our ideal gas law constant, so first we'll take the equation and manipulate, then we'll substitute our values in, and we get a value of R of 8.314 kilopascal liters per mole Kelvin. So this is our value of R in all cases. So now let's take our values and solve. So here we want to know the volume of a certain amount of gas and temperature and pressure. Okay, first thing we do is we always write down our givens, right? And so we're told our pressure. We want to find our volume. We're told our amount of gas. R is a constant, and it's always going to be equal to that. We're told our temperature in Celsius, so we have to make sure to remember to convert it to Kelvin. Then we can take our ideal gas law, manipulate for an unknown variable, substitute in, and we get our volume. Now, I can take my ideal gas law and I can manipulate it in a couple of different ways. One of the ways is, rather than use moles, I can use the relationship of what moles is, where moles is my mass divided by my molar mass. And so I could get an ideal gas law where PV equals mass times RT over my molar mass. Okay. Now, I could further take this equation, because I know density is equal to mass divided by volume, and I could manipulate it, and therefore what this would allow me to do is to solve for the density of any gas at its pressure and temperature. And so what we can see is that the density of a gas is related to its pressure and its temperature, because the molar mass is constant and R is constant. So, to what temperature would 15.4 grams of carbon dioxide have to be heated to have a pressure of 32 kilopascals? Okay, we write down our givens. In this case, we're looking for temperature. We're going to write down our modified ideal gas law equation. We're going to isolate for the variable of interest, substitute in, and solve. And so we get a temperature of negative 8.19 degrees Celsius. Likewise, we could also use our modification. What is the density of fluorine at SATP. SATP is similar to STP, except we change our temperature and pressure slightly. And so our temperature is 25 degrees Celsius and our pressure is 100 kilopascals. Okay, we can calculate our molar mass of our fluorine. We have our R value. Make sure to always write down your units. We substitute in, and we're left with, we can solve for our density. Now, one of the things that we can use our ideal gas law is to determine the molecular formula of the gas. So if we have a gas and we know its density, and we're asked to determine its molecular formula, we're given our percent composition, we can solve for our molecular formula. Now, we will remember when we did our empirical formula, we used a chart where first we listed our elements, then our percents, then we assumed we had 100 grams, so therefore my percentages and mass are equal. I'm going to convert that into moles, and then I'm going to look for the lowest number of moles, and I'm going to divide all of my values by that to get my mole ratio. And so now I have an empirical formula, CH3. Remember, to get the molecular formula, I have to divide the molecular formula, the molar mass by the empirical mass. So the empirical mass of this would be 15, so I need to know my molar mass. Well, we can use the information with our modified ideal gas law to get our molar mass, because we're given our pressure, we know our ideal gas law, we know our temperature, and we know our density. So I can take my equation and manipulate it and solve for my molar mass. So we get a molar mass of 30.4 grams. So now I can solve for the factor that I reduced by to go from my molecular formula to my empirical formula. By taking my molar mass and dividing by my empirical mass, and I get a value of 2. So therefore, my molecular formula is C2H6.